Atmospheric pressure. So the Earth is surrounded by an atmosphere, and it's air. We think of air as being light, right? But air does have mass, and you get a couple of miles of air above you, and it does exert pressure. We don't feel the pressure from the air because we always have that pressure with us, right? And so we're used to it. But the pressure of the atmosphere does vary a bit. If you watch the weather, the weatherman will say, well, there's this high pressure front coming down here, and there's a low pressure front over here. The differences in atmospheric pressure are what drive our weather, cause wind and move things around. And so we usually associate high pressure with clear weather and low pressure with unstable weather. Who knows what might happen? It might rain, might not. The number of gas particles in a given volume of air, so if you filled a container with air at sea level, and then you went up to Grant Grove, which is like 7,000 feet above sea level, and filled the same container with air up there, and were able to count the particles, you'd find that there's fewer particles in the same volume of air at a higher elevation. The pressure is lower. And we notice that when we go up into the mountains, because you get out of breath more easily because the concentration of oxygen is lower. There's just fewer oxygen molecules. And so you have to breathe more to fulfill the requirements of your body. So the atmospheric pressure decreases with increasing altitude. Here's an illustration of pressure. Here we have 2 mason jars, and this one has this one has some gas molecules, and this one has more gas molecules. So the pressure in this one with the few particles is going to be lower, and the pressure in the one with more particles is going to be lower. This is also related to density. Density is mass per unit volume. These gas particles have mass. They're occupying the same volume, but there's more particles here. So there must be more mass here. And so this container is going to have a higher density than this container. Have you ever had your ears pop? Yeah. You go up to Grant Grove, your ears pop on the way up, and then they need to pop on the way down. Mine don't pop well coming back down. It's very annoying. What happens, inside your ear, you have the eardrum, and that's an airtight seal between your outer ear and your inner ear. And then you have this eustachian tube that goes down and actually opens in the back of your throat somewhere. Well, what happens when you go to higher altitude, well, let's first talk about where you are right now. The pressure inside your ear is equal to the pressure outside your ear. When you go to higher altitude, the pressure outside your ear gets reduced because atmospheric pressure is decreasing as you go higher in altitude. Well, that causes an imbalance, and your eardrum, which is flexible, is going to bulge outward. That doesn't feel very nice. If you have an ear infection, it can be excruciating. It can be really, really painful. So it bulges out. How do you deal with that? Well, you yawn, or you chew gum, or you talk, right? You move your jaw. That helps to open your eustachian tube and allow this excess pressure inside your ear to come out. And you hear that as a popping sound as the air comes out. When you come back down from high elevation, the reverse happens. And now you have low pressure inside your ear and high pressure outside your ear. That can also hurt. And then again, you have to yawn or chew gum or something and get that to pop and let air into your ear. And this whole situation is why babies often scream on airplanes. It's because their eustachian tubes are tinier than ours, and they get these imbalances that are harder to take care of, and it's very uncomfortable. Yes?
When I was younger, I wasn't that smart, and I decided I wanted to see how long I could go without popping my ears. That was a very bad decision when I eventually popped my ears. And it all released at once. It was rather painful.
Yeah, that would be painful. Yeah. Because you can resist that and just let the pressure build up, but it doesn't feel very good at all.
When my family and I scuba dives,
Mm-hmm.
we usually pop our ears like every 10 feet of depth.
Yeah, you would need to do that. Yeah, we'll actually talk about scuba diving in a minute.
So like sometimes when I get on a plane, I go straight to sleep. My ears pop themselves when I go up.
Your ears will pop by themselves if the pressure difference is significant enough. Now, airplanes, the cabins are pressurized because if they weren't, everybody would pass out during the flight from lack of oxygen. Well, yeah, sometimes that might be a blessing, but you definitely want the captain to be conscious. And some people have a lot more trouble with that than other people. If you have any sort of a head cold going on, it's going to be a lot harder to pop your ears, and that can be a problem. So, how is atmospheric pressure measured? The original way is with a mercury barometer. And a mercury barometer can be made by taking a long glass tube full of mercury and inverting it into a dish of mercury. Have you ever done this with a cup in the bathtub or in the sink? You take a full cup of water and you tip it over really fast and stick the top of the cup in the water. And the water stays in the cup. And it's like, well, cool, look at that, right? It's really neat. With mercury, most of the mercury will stay in here, but you will get a vacuum forming up here if the tube is long enough. And the reason for that is that mercury is a lot more dense than water. The density of mercury is about 13 times larger than water, and so it's much heavier. So Torricelli I think he was Italian. He was a scientist who worked with a mercury barometer, and what he found was that regardless of the size of the glass tube, the diameter of it, the atmosphere would support 760 millimeters of mercury, approximately. And that if you take this barometer up a mountain to higher elevations, the column of mercury gets shorter. And when you bring it back down to the original elevation, it goes back up to where it was before. The height of the column of mercury is a measure of the atmospheric pressure. The atmospheric pressure pressing down on this pool of mercury outside of the tube supports the mercury being held up in the tube. And so you've got the force of gravity pulling down on this mercury, and you've got atmospheric pressure pressing down on this and supporting that. So we have this odd unit, millimeter of mercury, which when you just look at it, it's like that's the length of an element. That's a weird unit, isn't it? But it's literally from measuring the height of a column of mercury with a ruler. Very, very simple device. So millimeter of mercury. Average atmospheric pressure at sea level is 760 millimeters of mercury, and that's an important number to know. Higher the pressure outside, higher the column of mercury. There's another unit, the torr, and this is named after Torricelli. 1 torr is exactly the same as 1 millimeter of mercury. So it's just another name for a millimeter of mercury. Yes?
Why can't they use just regular water in the tube?
Okay, you could make a barometer with water, and it would need to be about 32 feet tall.
Explain it.
Yeah, it's like 3 stories or so. Not very practical. Yeah, so that's why they use mercury. Yes?
Why that tall than mercury?
Because mercury is more dense than water, and so a column of water weighs a lot less than a column of mercury.
So you need 32 feet in the water to get that same pressure then? Mercury?
Right. Yeah.
So then could you use something similar to mercury on the periodic table?
The problem is that there aren't very many dense liquids at room temperature. And so mercury worked really well. Now, we don't generally use mercury barometers anymore. We used to have them in the classrooms. In fact, if you look in the back corner there, that kind of yellowish stripe, that's where the mercury barometer was. But people are afraid of mercury and they felt it was unsafe, so they took them all out.
Where
They're really
can you
pretty
find
cool.
mercury naturally?
I don't think you find elemental mercury anywhere, really. I think you have to isolate it from mercury compounds. Yeah. It is pretty. It's really neat stuff. Unfortunately, it's also toxic. There are some other units of pressure. And the reason we have so many different units is because different sized units are useful in different fields. So the weatherman talks about barometric pressure in terms of inches of mercury. So average barometric pressure at sea level is going to be 29.92 inches of mercury. If you convert 29.92 inches into millimeters, it's 760 millimeters. It's, again, a length of mercury. Torr, just another name for millimeter of mercury. Pounds per square inch is one you're probably familiar with if you've ever filled a bicycle tire or a car tire. PSI stands for pounds per square inch. Atmospheric pressure is 14.7 pounds per square inch. Pascal is the SI unit. We don't use that much in chemistry, but there it is. And atmosphere is another one we use a lot. 1 atmosphere is the atmospheric pressure at sea level, and that is equal to 760 millimeters of mercury, or 760 torr. Notice that the 760, that number is exact. So it does not just have 2 significant figures, it's an exact number. So we need to be able to convert pressure units. So local weather report says the barometric pressure is 30.44 inches of mercury. Convert it to PSI. So this is the way that pressure unit conversions are often expressed. And I'm going to just tell you right now, this first one, that first line, you should memorize that. 1 atmosphere is 760 torr, which is the same as 760 millimeters of mercury. That's exact. If you need one of the ones on the bottom here, on an exam, I'll give it to you. But you should memorize the 760, because we're going to use it a lot. So this is just dimensional analysis. The way the pressure unit tables are set up, you can always do this in just one step. So I'm going from inches of mercury to PSI. I'm going to divide by inches of mercury. So I got my units in there. This tells me that 1 atmosphere is equal to 101,325 pascals, which is equal to 14.7 psi, which is equal to 29.92 inches of mercury, which is equal to 760 millimeters of mercury, which is equal to 760 torr. They are all equal to each other. So I can just choose whichever 2 that I need and make a conversion factor. So for PSI, I'm going to use this number, and actually it's 14.69. We know it to more decimal places than that, but the 14.7 causes a problem in this problem. 14.69 PSI, that's not an exact number. The only one that's exact is the 760. And then I want 29.92 inches of mercury on the bottom. And then I'm going to get out my calculator, 30.44 times 14.69 divided by 29.92. And how many significant figures should my answer have? 4. So I'm going to report this as 14.95 PSI. The problem with using 14.7 is then you've got your conversion factor limiting the number of significant figures in your answer. We don't want that. We'd like our original measurement to limit the number of significant figures. And so this was a poorly set up example that I need to remember to change for next year. Any questions? So barometer is used to measure atmospheric pressure. What if we need to measure pressure inside of a container? Well, we can use a manometer. A manometer consists of a U-shaped tube containing usually mercury, but you can do it with other liquids. So this one has mercury in it. And one end of this tube is connected, is open to the atmosphere, the other is connected to the container whose pressure we're wanting to measure. If both of these sides of the U-tube were open to the atmosphere, what would we expect the levels of this liquid mercury to be? Equal. If you take a garden hose, excuse me, I don't usually get choked up about garden hoses. If you take a piece of clear tubing and put some water in it and you hold it up, you can see that the levels of the water are the same because it's trying to go to the lowest point. Here, though, one side is lower than the other. What's causing that? The pressure. There's high pressure in here. You think of someone blowing down on one side, right? It's going to force the other side to go up. The difference in the pressure can be measured by measuring the difference in the heights of the columns.
And then you just convert it?
Yeah, so you could measure this with a ruler in millimeters, and there you have the difference in millimeters of mercury. Now that's not telling you the pressure here. It's telling you the difference in pressure between the inside and outside. If you know what the atmospheric pressure is, then you can add that difference and you get the pressure inside. Any questions? Now, we do not typically measure pressure using manometers and mercury barometers. We have electronic devices that measure pressure now, but these also work. Yes?
Okay, you said about the atmospheric, that's not giving you the pressure in the container. What did you?
The difference here, H, the height difference, gives us the difference between atmospheric pressure and the pressure inside the container. In order to measure the actual pressure here, we need to know what atmospheric pressure is. And then we add this to get the pressure inside.
Okay, so it would be like, let's say, the atmospheric pressure is just like 760 mmg, and then we have like another 40
Right.
going up, then so it'd be like 800.
Yeah, so if we said, well, this is 70 millimeters of mercury. And the outside pressure right now is, is just, we're at sea level, and it's 760 millimeters of mercury. Well, then the pressure inside is going to be the 760 plus the 70, so 830 millimeters of mercury.
Now, how do you take into account if you're not at sea level?
Well, you would have to measure the atmospheric pressure.
Okay.
How could you measure the atmospheric pressure? With a barometer. What's really cool to me about all this gas stuff is they were doing these experiments like back in the 1600s. They didn't have electricity. They didn't have technology. They used simple things like rulers and glass tubing and mercury. And they studied all kinds of cool stuff about gases. Any other questions?